All right, so we are going to keep on talking about logarithmic functions. Today we're just going to focus on the graphs. And so there's a whole bunch of information in this table, so I'll kind of go over it with you. So first, just this generic form of a logarithmic function, the base has to be positive and the base cannot be 1. And then this number in the front can't be 0 because then it would just be a horizontal line. It wouldn't be a logarithmic function. And one other thing is that the argument part, it must be greater than 0, which kind of takes you to the domain. So some of the last things we're going to do today is find the domain of logarithmic functions. And so if it's something other than x, then that domain is going to change from problem to problem. The range, however, for every logarithmic function, the range is going to be all real numbers, or negative infinity to infinity, because you're going to have an arrow going up and an arrow going down. All right, so if that first number in the front is positive, then it's going to be similar to the parent function of a logarithm. So that basic shape, you'll see that over and over and over again. If that's a negative in the front, what transformation is that if there's a negative in the front? Reflection on the x-axis. So that's what this one is, the logarithm that's been reflected on the x-axis. All right, and so a logarithmic function is either always increasing or always decreasing. So if it's always increasing, it's going to look like this one. Always decreasing is going to look like this one. And so because the function never changes from increasing to decreasing or vice versa, there is no relative max or relative min. So you cannot find it. It doesn't exist. And then a logarithmic function is always concave up or always concave down. And so there is no point of inflection. Now, my calculus class just learned about points of inflection today, and you guys learned about points of inflection like at the very beginning of the year. So you know a little bit more than they do about points of inflection right now. But a point of inflection is a point where the function changes from concave up or concave down or vice versa. So because the concavity is going to be the same, you're not going to have any of those. All right, and then for the end behavior, to describe the left side of the graph, this is the limit we're going to use. The limit as x approaches 0 from the right describes the left side of the graph. And then the right side, like normal, is going to be the limit as x approaches infinity. So the reason we don't go to limit as x approaches negative infinity is because it doesn't get that far. Like it starts and stops at 0. So that's why we use 0. And because you have an arrow going up and an arrow going down, those limits are always either going to be infinity or negative infinity. All right, so let's do some limits. So for example 1, we have the graph of the function, and the left side is this limit. And so you just basically look at your left arrow. Since that left arrow is pointing down, then that's going to be negative infinity. All right, and then the right one, we're going to have to write our limit. So on the right is the limit as x approaches infinity of f of x. What do you guys think that's going to be? It's going to be positive infinity. Good. Do you think it's possible on these logarithmic graphs for them to both be positive infinity or both negative infinity? No. So one will be positive and one will be negative infinity for your end behavior. All right, so on B, we're going to find the left end behavior is going to be the limit as x approaches 0 from the right of h of x. So to figure that out, you're just going to look at the left arrow, the left side of the graph. Since the left side is pointing upward, that limit is going to be infinity. And then the right is going to be the limit as x approaches infinity of h of x. And because that arrow is pointing downward, that's going to be negative infinity. Now, on your worksheet, I think all of these, you're not going to have the graph. You're just going to have the equation. So you can either remember what the logarithm graphs look like or come back to this table, and eventually you're going to remember what they look like. But this one has a positive number in the front, so that's going to be the basic parent function of a logarithm, which is going to look like that. The left side of a logarithm is always the limit as x approaches 0. Well, unless I shouldn't say always, because these could shift left and right, but none of these that we're doing have shifts right now. All right, so since that left arrow is pointing downward, it's going to be negative infinity. And so we already know the other one is going to be positive infinity because they cannot point in the same direction. All right, so what questions do you guys have about end behavior?
That was a -2, would it be like B?
Yes, ma'am. Okay, so on example 2, we have some graphs, and then one of them, the last one, we just have the equation, and we're going to tell concavity and if the function is increasing or decreasing. So on A, would you guys say that's concave up or concave down? Yeah, it kind of looks like a smile. Half of a smile is going to be concave up. All right, is the function increasing or decreasing? Decreasing. Now that is not the way it's worded on your worksheet. So it has a statement, something like that it is decreasing. But for concave up, is the rate of change increasing or decreasing? It's been a while since we talked about that. Increasing. So concave up, the rate of change is increasing. So this function is decreasing at an increasing rate. That's how it's worded on your worksheet. And when we first learned this, like I said, it's been a while. Whenever those two things were working against each other, the graph starts to flatten out, and you can see that the graph is flattening out, so they should be working against it. They're working together, then the graph starts getting steeper and steeper and steeper. All right, so on B, this one is concave down, and the graph is increasing. So this one you would say is increasing at a decreasing rate. All right, so you guys try to see on your own. So decide if the graph is going to look like A or B. Do a little sketch of it, and then circle. All right, any questions on concavity? Okay, and then for example 3, these have varying levels of difficulty. Like sometimes it's super obvious, and then sometimes like when we get to the third one, the fourth one, it's a little bit tricky. So that tells you that these are all logarithmic functions. So for logarithmic functions, the y values are evenly spaced, so going up or down by the same value every time. And then the x values are found by multiplying by something each time. So we have this missing value as an x, and so we're going to find what it is. And sometimes it's fairly obvious. So what are we multiplying by on the first one? So what should k be? Yeah, so that's like that one, semi-obvious. All right, what are we multiplying by on the next one? 3. So what should k be? 2. All right, this one is a little tricky. So that y's are equally spaced, but you don't multiply by something each time to get the next one on the x's. And we did some like this, just a few, when we did exponential. Do you guys remember what we did if you couldn't see the multiplication? You subtracted. So what we're going to do now on those, it was the y's. So we're going to find the first differences of the x's. We haven't done this with x before. So we're just going to take one and subtract the previous one. So on this one, the x's, you added 1, and then you added 2, and then we're going to add something else, and then we're going to add something else. And then what ended up happening when you look at these numbers, you're multiplying by the same thing each time. All right, so if I multiply 1 by something to get 2, and then multiply by that same thing, what would I get here? 4. And then I multiply again, and that would be 8.
Wait, how did she get 4?
Okay, so I'm finding the first differences, but you can't really find one. If I know this is logarithmic, those first differences should multiply by the same thing each time. And so I know that that's times 2, so that needs to be times 2 times 2. All right, so what should k be? Yep. Tricky. All right, now this next one, we are multiplying by the same thing each time. It's just kind of harder to see because they're powers of e. So when you're multiplying powers of e, what do you do to the exponents? Anytime you're multiplying and there's the same base, what do you do to the exponents? If I was going to multiply 2 to the third by 2 to the fourth, what would I do with the exponents? You would add them. All right, and so we are multiplying here, but what you see is the result of adding the exponents. So let's start with the 7 and the 10. What would you multiply e to the 7th by to get e to the 10th? E to the third. So that is what we're multiplying by each time. So what should k be? If I take e and I multiply e to the third by, it's e to the fourth. All right, so like I said, sometimes it's really obvious. Sometimes you have to get creative and dig into your mathematical knowledge. All right, and then this very last example, we're going to find the domain and range of some logarithmic functions. Now, the range of every single logarithmic function in the world is all real numbers, or negative infinity to infinity. So we can go ahead and do that and not have to worry about the range, because I know I'm going to have an arrow pointing up, I'm going to have an arrow pointing down. Right? And then for the domain, it can change from problem to problem. And so basically what this argument is, it must be greater than 0. So if it's just x, that's just x is greater than 0. Or if you prefer interval notation, it'd be from -0 to infinity. Now when I get to b, I'm going to take that x minus 3. I'm going to say that it's greater than 0. And so what would you get if you solve that for x? Good. That's your domain. X is greater than 3. Or if you wanted to do interval notation, it would be from 3 to infinity. Okay. So if there's something added or subtracted to your X in your argument, then you need to take that and say that whatever that argument is greater than or equal to 0. And then do whatever you have to do algebraically to solve that for X. All right, what questions do you guys have? Okay, don't be surprised if on your worksheet there are a couple that really challenge you. It's okay. Like there's a couple on here that I don't expect you to 100% understand at this moment, but I just want to give you a little sneak peek of stuff that's coming.